Hello everyone, you are welcome to today's analog communication tutorials on the topic angle modulation. So without wasting much time, let's go straight to the point so that we can do as much as we can and then we solve some examples. So we have already studied amplitude modulation, and when we started, I said that we have an amplitude modulation, phase modulation and frequency modulation. But aside the amplitude modulation, the other types of modulation in continuous wave modulation is the angle modulation, right? So the angle modulation refers to as the process in which the frequency or the phase of the carrier signal varies according to the modulating signal or the message signal. So basically, the combination of the phase modulation and then that of frequency modulation is what we refer to as the angle modulation. So the standard equation for an angle modulation, is S equal to, or let's say S of t is equal to AC cos into brackets theta I of t, where theta I of t is the cos parameters, right? So let's break down the various parameters that you can see here. The AC is equal to the amplitude modulated wave. The theta I of t is also equal to the angle of the modulated wave. So knowing that these are the parameters which is inside the cos over here, let's look at the various division of the frequency or the angle modulation. As I said earlier on, the angle modulation has been divided into two, which is the frequency modulation and the phase modulation. So now let's take them one after the other. Let's pick the frequency modulation. So the frequency modulation is a process by which the frequency of the carrier wave is linearly varied with respect to the message signal. So based on this, we can say that in the amplitude modulation, the amplitude was the one which was changing, but in frequency modulation, the amplitude and also the phase constants, but the frequency of the carrier wave will be changing according to the instantaneous change of the message signal. So let's take very good note of it. But without wasting much time, let's go ahead and do some mathematical analysis on this. Before that, you have to keep in mind that the equation for instantaneous frequency, which is Fi, that we are going to represent, this is the instantaneous frequency. This is where the change in frequency comes in, right? So if I have my carrier frequency to be Fc, if there's a change in frequency, let's say an increase in frequency, it will be increased by a particular change in frequency. And that change in frequency, it's equal to Kf m of t. That's something that you have to take note. So looking at it, I can write it as Fc plus Kf m of t. The Kf m of t represent the change in the original frequency, and the original frequency or the initial frequency was f of Fc. So Fc is the carrier frequency. The Kf is the frequency sensitivity. So this Kf here is the frequency of sensitivity. The frequency sensitivity. And then as we know already, the m of t is the message signal. So let's go ahead and do some small mathematical analysis. As I said earlier on, the S of t for the FM modulated wave is equal to AC cos theta I of t. So this theta I of t is an angular displacement. Angular velocity, omega I, is equal to angular displacement, let's say this angular displacement over time, right? So the time is a change in time, let's say that way. So in doing this, we can say that this angular displacement is equal to omega I change in t, right? And when we want to find the integral of both sides, we can say that this integral of I of t is equal to the integral of omega I dt. And this omega I can also be represented by 2 pi fi dt. You have to take note. Where the fi represents the instantaneous frequency that I wrote over here, which is equal to fc plus kfm of t. Based on this, we can substitute this into this equation, and we are going to get, when I find the integral of this, I'm going to get integral of theta I of t to be equal to integral of 2 pi fi. Integral of 2 pi fi. So doing this, what we can do right now is integral of this one is supposed to give us theta I of t, which is equal to 2 pi fi. And now we know that our fi is equal to fc plus kf m of t. That's the frequency sensitivity. Therefore, I can see that my theta I of t is equal to 2 pi out integral of fc plus kf m of t. So substituting this into this standard equation AC cos theta I of t, I can say that this one can be written as S of t equal to AC cos into bracket 2 pi integral of fc plus 2 pi kf integral of m of t. I hope you have seen the expansion that I've done here. So if I'm doing this integral over here, I'm going to get S of t to be equal to AC cos 2 pi, the integral of f of fc dt is equal to fct plus 2 pi kf integral of m of t. So this is one standard equation for an FM wave. But we can further simplify it to know some representations over here. Let's take a look at it. We know that our m of t is equal to am cos omega mt because it is the message signal. So based on this, I can rewrite this one as AC cos 2 pi fct plus 2 pi kf am cos, that's the integral, cos omega mt. So let's take this only and work on it. When we are done, we will substitute it over here. So taking integral of cos, we know that omega m is equal to 2 pi fm. And then remember there's a t over there. So cos 2 pi fm of t dt. When we are doing the integral, we are going to get sine 2 pi fm t all over 2 pi fm. So based on this that we have over here, we can substitute it back into this equation. When we do that, we are going to get AC cos 2 pi fct plus 2 pi kf am sine 2 pi fmt all over 2 pi fm. 2 pi will go into 2 pi, and now we are going to get AC cos 2 pi fct plus kf am over fm sine 2 pi fmt. Let's kind of simplify it. So now we are aware that omega c is equal to 2 pi fc. Therefore, we can replace this by this. Omega m is equal to 2 pi fm. Therefore, we can replace this by this. So when we write it, we are going to get AC cos 2, let me go here, cos omega ct plus kf am over fm sine omega mt. Right? So this is basically a simplification of this, which is S of t to be equal to this. Now that we have this, let's go ahead and then look at whatever is the coefficient over here. Whatever is this coefficient. Now we can say that this B is equal to kf am over fm. And this B, we call it modulation index of an FM wave. So take note of this. Modulation index of an FM wave. So we can further simplify this in such a way that this KF AM is equal to change in frequency or the frequency deviation. Take note, this is frequency deviation, right? And then the FM is equal to FM. So if we are rewriting this, we are going to get B is equal to this frequency deviation over FM. So you can establish about 3 equations here, which is frequency deviation equal to the modulation index of the FM multiplied by FM. There's another equation as well. So based on this, I can rewrite this standard equation to be equal to S of t is equal to AC cos omega ct plus beta sine omega mt. And then we are done. So this is actually the standard equation for an FM wave. The standard equation for an FM wave. But before we proceed, I would like you to take note that the frequency deviation, right, is the difference between the FM modulated frequency, which is the instantaneous frequency, and the normal carrier frequency, right? That is what we call frequency deviation. That is the change in the F that I've done over here. Just take note of it. And this frequency deviation is equal to the product of KF and then AM. And it's also the same as the modulation index times FM, in case you have it, based on this establishment. FM can also be divided into 2 parts, which is the narrow band FM and then the wide band FM. And we will talk about them later. So thank you for watching and see you in my next video.